So Politecnico di Milano is part of the Stardust project, which is a H2020 research network. Can you tell me a bit about what's your role?
Yes, we are proudly partner of Stardust Reloaded. We are also partner of another innovative training network called Utopia, which is also coordinated by Strathclyde University. I said we are proudly partner of Stardust because we have been one of the founding members. Me being involved in former Stardust, because Stardust Reloaded is, let's say, stems from Stardust 1.0, which was a previous training network under the 7th framework program. At that time, Horizon 2020 was called FP7.
Okay.
And so, as I said, we are proudly members because we really think that Stardust is a nice exercise to train the future generation of engineer, physicists, mathematicians on emerging topics in the space field, which are topics that are likely not faced in regular classes when you are at the master level at universities. My role, I'm one of the few scientists in charge of Stardust, which means that I take part to the supervisory board of the network, and as such I'm also advisor of one of the early stage researchers. Stardust is made of 15 early stage researchers, which are freshly graduated at master level students with up to 3-year experience after graduation. At the moment, Stardust has, let's say, 2 large groups in terms of ESRs. One group is made of mathematicians and the other of engineers. And it's nice that the 2 groups are interact each other, and they try also to have a beneficial mutual exchange, because the 2 groups come from different schools of thought. And I think it's constructive for the sake of the whole network. Here in Polimi, we are responsible for one of the work packages of Stardust. As you know, Stardust involves, generally speaking, space debris and small bodies. We are not involved in the space debris part of the network, but rather we are involved in the small bodies. Now, while the former Stardust was more about planetary protection, so seeing, let's say, conceiving the small bodies as a threat for humans. We have proposed, back at the time we wrote this proposal, I personally proposed to Professor Vasilia, the coordinator of the network, a different change of paradigm. And I proposed to see the small bodies as resources. And in fact, now the work package we are part of is called minor body exploration and exploitation. I'm still convinced that minor body are valuable resource for humans. Moreover, they are very valuable scientifically because they are infinitely many bodies and diverse. So there is much scientific interest to visit them. And as a side effect, there is also technological interest to exploit them in terms of resources.
And can you say something more specific about your working package and how this is related to other works you're conducting?
Yes. So the work package we are involved in is about, as I said, small body exploration and exploitation, with a class of spacecraft that is following a current trend in space engineering. Namely, there is a paradigm shift now occurring in space engineering, and in order to allow small institutions research centers, even universities, to enter the outer space, the entry level must be lowered, because nowadays the deep space has been for half a century a prerogative of large agencies like NASA, like ESA, JAXA. So I'm pretty much convinced that in order to, let's say, democratize the deep space, the entry-level cost must be reduced. And this is happening by using miniaturized versions of larger space probes that are called nano spacecraft, nano satellites, or if they fit a specific form factor, they are even called CubeSats, which are little modules made of cubes, which are 10 centimeters side and 1.3 kilogram weight. So in Stardust, we are studying the autonomous operation of a miniaturized spacecraft around a small body, around an asteroid. So suppose you are flying a mission, a miniaturized mission around an asteroid, you may want the spacecraft to self-operate in terms of self-determining the its orbit, its flight, its position, totally in autonomy, because you want to get rid of costs related to the operation from ground.
Okay.
And that's why we are involved in this work package. We study the so-called GNC, where GNC stands for Guidance, Navigation and Control of miniaturized probes around small bodies in the deep space.
Mm-hmm. Okay, and I recall you talking about autonomous navigation, making use of planets as
lighthouses. Yes.
And would that be part of Stardust, or is it more?
Well, no, that is actually part of another project I'm about to start in next few months, which actually got a prestigious award by the European Research Council. I've been awarded an ERC Consolidator grant, which is a grant that is given to researchers at their mid stage of career. You can apply if you are from 7 to 12 years from since the PhD graduation. So I applied actually last year in 2019 to this round of Consolidator grant, and I was happily one of the few that got the grant, because this is very, very competitive. The success rate for this year has been 12%.
And was this part of H2020 or is something outside?
ERC is a small piece of H2020 framework. So coming to your question, the deep space navigation and using the planets as lighthouses to triangulate the spacecraft position is not part of Stardust, but is rather part of Extrema. Extrema is the name of my project, of the ERC project I'm PI
what does
of.
it stand for?
It stands for Engineering Extremely Rare Events in Astrodynamics for Deep Space Missions in Autonomy. Okay. There's no one-to-one association between the acronym and the initials of the title. This is one of those cases in which I found a nice word first, and then I tried to fit a nice title with catching some of the words that make it. But this is a current trend in our field, or in almost all fields. The acronym matters, actually. So in that project, it's something that we can see it in both ways. Either it stems from Stardust or it contains Stardust in it, because Extrema is about forging a new class of space missions. Namely, I'd like to see space missions, because of the costs associated with the ground-based operations of the spacecraft in cruise mode, in deep space cruise, the only way to cut these costs is to let them go. Mm-hmm. Now, think of a deep space cruise. It can last months, if not years. So we take 6 months to go to Mars. We can take years to get to an asteroid. So with current approach, you have to babysit your spacecraft when it's in
like Rosetta was.
Like Rosetta was. So from time to time, you have to reconstruct the spacecraft position by involving the ground-based assets, which means involving antennas and dedicated team of people to work on the autonomous navigation. Then once you determine the state, the spacecraft state, you reconstruct the position and velocity of the spacecraft, you have to elaborate the so-called guidance, which is a plan that the spacecraft has to follow in the next few days. And then you have to actuate the plan by using onboard thrusters. So the ambitious project, the ambitious idea that I had and that I proposed to the European Research Council was to implement all of these tasks on board a miniaturized CubeSat, miniaturized spacecraft with, by definition, limited capability in terms of computational time, thrust authority, power production, telecom, and so on and so forth. Why this? Because nowadays in our community, much effort is being spent in miniaturizing the probes. We are experiencing a change of paradigm from monolithic spacecraft worth the whole mission can be worth like €1 billion to cheaper, lighter, and faster probes. But however, much effort is being put in our community to miniaturize the probes, but the concept of operating them is being kept the same. So there is actually a huge gap in the autonomy level that you can achieve when it comes to operate a CubeSat. So since all of our communities is working on this concept, I want to actually to move away from this and grant higher level of autonomy in deep space. In fact, I want to work in this area. This is how the solar system has been explored in half a century, more or less. This is what's happening now. This is the mass at launch and the level of autonomy on the y-axis. I want to work here, and if this is successful, the impact will be on bigger spacecraft, better performing, because by definition, a CubeSat has a skeletal budget, and if we are successful, because of the very strict budget of CubeSat in terms, for instance, of control authority, if this concept proves true, it will be valid also for better performing spacecraft. And if we think of this paradigm, the operational costs don't scale, but only the system's costs scale. With my project, I want to scale the operation costs as well, so granting what I call full mission cost scalability. That's the key and the potential of the project.
And do you see some challenges in this miniaturization, which is not directly what you're doing, but let's talk.
Yes.
And specifically focusing on outer space, because we could talk a lot about space debris and the mega constellations, but can you say something similar about outer space?
Yes. There are pretty huge technological challenges that needs to be solved. CubeSats, they originated in the early 2000s as a matter of university exercise. Then, half of them failed, but the other half, let's say, they did something. So there was some value. This was the first wave of CubeSat. The second wave came from the students that were experienced the CubeSat exercise for their thesis. These students graduated and they founded small companies, right? And the CubeSat became an industrial standard. And the second wave was, in fact, what we have nowadays, that the CubeSat is actually an industrial standard, and it's powerful because of fast development time and reduced costs to low Earth orbit. Now, the third wave will involve actually to bring this little piece of hardware and put it in the deep space. Mm-hmm. This is a big challenge because if we think, for instance, of power production, the power from the sun scales with the inverse square distance from the sun. So the farther you go, the less power you have. Communication. CubeSat don't have those big dishes mounted on monolithic spacecraft. Radiation shielding, because CubeSat in low Earth orbit are protected by Earth's magnetic field, but this is not the case of the deep space. Thermal protection, or let's say thermal stability. Accurate pointing without having, again, a magnetic field to rely of. Micropropulsion. Mm-hmm. CubeSats release in low Earth orbit they barely have no propulsion, because they are just released in a low Earth orbit. Whatever it is, they don't perform orbital maneuvers.
And they come down with the atmosphere.
Exactly.
Without the need to maneuver.
In the deep space, by definition, you must grant maneuverability of the orbit if you want to go from A to B in the deep space. Otherwise, you'll never reach your target unless you want to stay in the deep space, which is can have some value to do some astrophysics, for instance, but it's not, let's say, proper for deep space exploration. So if you want to visit some body. So as I said, attitude pointing and micropropulsion, and the astrodynamics also of interplanetary CubeSat, because this thing having very reduced budgets, you have to use also the orbital dynamics, and you have to explore the natural dynamics as much as you can. Mm-hmm. So these are the challenges up to me, and I'm not involved in the first that I mentioned, like power, thermal, communication, and so on. I'm more involved in the latter one. So in working with the astrodynamics, guidance, navigation, and control, attitude pointing, and so on.
Okay, so let's talk about hardcore astrodynamics, please. Let's go. So you worked a lot on ballistic capture, low energy transfers, and can we talk about how do they work? So
imagine you have a spacecraft that is approaching Mars, for instance. So when the spacecraft approaches Mars with the conventional approach, this is called patch tectonics, in which you get rid of the real nature of the solar system, and you try to decompose the solar system as a number of problems in which you have your spacecraft and one of the main bodies, like spacecraft and the Sun or the spacecraft and Mars. Mm-hmm. Now, this method is good. It worked for decades now, and it allowed us to visit actually the outer planets and the inner planets as well. But however, it has a, let's say, pitfall in it, because it automatically forces the velocity upon planet encounter to be big enough. And in order to achieve an orbit about the target, about Mars, for instance, you have to apply a pretty high maneuver, which means embarking much propellant on your spacecraft. Now, it came out since the end of 1980s, beginning of 1990s, that if you decrease the energy of the spacecraft, mechanical energy, so the sum of potential and kinetic energy, and you take into account more than one gravitational attraction acting simultaneously upon the spacecraft, well, weird phenomena can arise. So you can get something that was not even conceivable in the standard approach. This concept originated from Dr. Edward Belbruno at Princeton University, and he found actually a new class of transfer trajectories from the Earth to the Moon. In fact, in 1993, he was able to rescue a Japanese satellite named Haiten. It was not launched to reach the Moon because it was launched along with another spacecraft that went lost. And the Japanese wanted actually to reach the Moon with this spacecraft that was not designed to reach the Moon. So it didn't have any propellant on board. So in 1992, Dr. Belbruno, together with James Miller, they were at that time at JPL. They designed this new trajectory that was actually then implemented by the Japanese, and they allowed Japan to be the third nation actually after Soviet Union and United States to actually reach the Moon with this mechanism. Now, for many years, this was actually a pretty good achievement, and originated also another branch of research dealing with three-body problem, invariant manifold, Lagrange point dynamics, that had as, let's say, reference schools, one school in Europe, in Barcelona, made of mathematicians, applied mathematicians, and another school in the west coast of the United States between JPL and Caltech. And this went on, and actually back at that time, at the beginning of the 20s, I was working on my PhD, and in fact, I did my PhD on the controlled restricted three-body problem. As I said, at that time.
When was this? 2000?
Well, I started my PhD in 2004,
okay,
and I graduated in 2007.
And you've been in Princeton during the time?
I've been in Princeton in 2006, actually. Actually, in 2005 for a very short visit, in 2006 for a little longer visit of 4 months, and also in 2007 for another very short visit. But the most of time I spent, it was in 2006, which was by the way, the year of the World Cup, when Italy won the World Cup. So I'll never forget that. I was not even here. Anyway, so I went there and I tried to learn this mechanism from Dr. Belbruno. I think I succeed, because after a while I kept contacts with him. In fact, we published, I would say, we have something like 10 joint papers together. And we have very smooth relationship and friendship. And where did I come into play into this game? For many years, it was thought that in order to have this mechanism, you needed to have a four-body dynamic. So in the Earth-Moon transfer, you exploited actually the Earth, the Moon, and the Sun plus the spacecraft. So this was the game was made of these four bodies, of which one is massless, which is your spacecraft, and three bodies. And our community didn't actually think of applying this to planetary encounters. Well, together with Dr. Belbruno again in 2014, end of 2014, beginning of 2015, we actually published a paper on celestial mechanics and dynamical astronomy, a reference journal in my field, which was actually a breakthrough. In fact, we had our story was covered by also Scientific America, and because it was a pretty important discovery that for the first time we showed that you can actually get ballistic capture at Mars or at any planet. And this is also a small piece of Extrema. In fact, if we link this with what we were saying previously, these CubeSats, they don't have a huge control authority, so they cannot impart impulses. They cannot change suddenly their course of trajectory. So it seems that they are forbidden to reach orbits around planets. And here is where I linked my idea. So what I was working on in the last few years with actually my core business, which was highly nonlinear astrodynamics involving multibody problems. I was able to make this link, and I'm actually very happy of how it framed it in a single picture, because with the ballistic capture you can grant CubeSats, which have actually zero control authority, to enter temporary orbits around Mars.
Okay. So is Extrema reaching Mars, and if so, when? When is it gonna fly?
Extrema
or
is,
let's say, when is the first mission allowed by researchers such as Extrema going to reach Mars?
Well, Extrema is a project that deals with basic research. So unfortunately or fortunately, depends on the point of view, it's not going to end with the spacecraft. Mm-hmm. So Extrema is a key enabler for the basic, let's say, technology, quote unquote, that you need to have on this new class of spacecraft. When will this become a reality? I would say the pace in our field has become crazy. So nowadays we are experiencing concepts like constellations made of 1,000 of satellites, which were fiction until 5 years ago. So there is quite some momentum now in space, at least for what concerns the low Earth orbit. My vision is that sooner or later, this momentum will make it possible to have massive deep space exploration. So if I have to tell you a date, I would say that probably the second half of next decade of 2020s will be characterized by a number of miniaturized probes exploring small bodies, if not going to Mars, in order to perform some science and also support the settlements that are just a matter of time. But now we are fully determined. There is actually much motivation in the community now to bring humans on Mars. So in my project, I have 2030 there for self-driving interplanetary CubeSats. I would say that in 10 years' times, this can be a reality.
Right. Let's hope this happens, and
finger crossed.
Thank you a lot for your time, Francesco.
Thank you.